or at least I would like to do a recap of where we are and where we're going with the technology we're building, correct? So let me just start from the very beginning. So the entire universe in this class is usually some ambient metric space, M, with a distance rho on it, right? This is sort of the ambient space where things happen. Right, so these are ambient metric space. So you can think of these as Euclidean space, for example, right? So your points are vectors. Yep. Not necessarily. So if I say metric space, then yes, I'm asking for this to be a metric, meaning that it has to satisfy the triangular inequality. If I just say a space with a distance, then I don't need the triangular inequality. Okay, but for now we're going to put it there for convenience. Okay, so we have our ambient metric space, and inside our ambient metric space, we often have some shape that we're interested in. This sort of the underlying space that has the ground truth. So this is some X. And we're going to put it over here. So X inside of M is sort of the ground truth. And then near our ground truth X, we have the data that we collect. Right? So we have a bunch of points, little x. Correct. Right, so maybe you have little x in X. So X is the data. And the idea is that X and fancy X are very close. Okay? And then we want to infer things from fancy X from the data that we're collecting. So the first thing that we've seen is that one can approximate the overall shape of the ground truth building simplicial complexes on the data. Okay, so the first idea is that we can approximate the ground truth via simplicial complexes on the data. Complexes on X. Right? So we've seen sort of a couple of flavors of what that looks like. We've seen the checked complex. Right? Which is denoted C alpha X. And it is defined as the collection of finite subsets. Let me just put it like this. So subsets of X, the data is assumed to be finite. So we just need this guy to be non-empty. So that if I intersect all the balls of radius alpha center at points in sigma, I get something that is non-empty. Right? In other words, I have a vertex in this simplicial complex per point in my data set. I have an edge if the two balls centered at those vertices intersect, and so on in higher dimensions. Okay? We also have the Rhibs complex. Which is the collection of subsets of X, again, this is non-empty, that have diameter less than alpha. Right? So that the maximum distance between any 2 points in sigma is always less than alpha. And we've seen sort of several properties of these constructions, right? So for example, here we need to think about balls in the ambient space M, and that can be complicated to compute. We gave you sort of a cheap way or a cheap approximation during the computational activity last time, but this is in practice hard to compute. But we have sort of good theory about this type of complex. So in particular, we have this is, again, hard to compute, but the theory is nice. And by that, I mean things like the Baby-Nair theorem. That says that if you start with your data set inside Euclidean space, then the check complex and the union of balls around points in X have the same topology. Have the same topology. So they have the same shape, more or less speaking. Yep. Yeah, this is for, in particular, there is a theorem where this is any topological space, but I have to tell you some things about these intersections. And we don't care about those conditions right now, but properties exist where you don't have the Baby-Nair theorem, but you have the full Nair theorem. So here's a remark that I think I didn't mention at the time where we introduced these complexes, and is that, so say that you compute the check complex, or no, let's say that you compute the Rhibs complex, right? Strike 3. So then we compute the Rhibs complex, right? So what we're saying is that the maximum distance between any 2 points in each simplex is less than alpha, right? So in particular, the balls of radius alpha intersect. In other words, this is contained in here. Let me know if that makes sense to you. Right, so how do we know that? So take a simplex in here, right? So say that you take an n simplex. So what does that mean? It means that the pairwise distances between any of them are less than alpha, right? So in particular, this point is in the ball of radius alpha around J. Around xj, right? So again, take any n simplex in here. Notice that for any 2 points, the distance between them in here is less than alpha, because that's what characterizes the Rhibs complex. And in particular, this condition tells you that this point is in the alpha ball around this guy, or conversely, that this point is in the alpha ball around the other guy, okay? So in particular, x0 is going to be in the alpha ball of everybody, right? So that means that the intersection is not empty. So in particular, alpha is also in here. So x0 is in the intersection, say from I equals 0 to n of b alpha k j I. Okay, so we have this complex that is easy to compute. We only care about pairwise distances. This has better theory, and we know that this is contained in here. And now using triangular inequality, and that's where we need metric, one can show that this is also contained in Rhibs, but now 2 alpha of x. Okay, so these complexes are easier to compute again, but they don't have as nice properties as the check complex, which is here in the middle, but one can sort of interleave it between the Rhibs complexes. Okay, so many times in applied topology, what people do is they use the theory they know about this, but then in computations, they actually use the Rhibs complex and then go from one to the other using these inclusions. That's the typical trick. Okay, so we've also, right, so we went from data near the underlying ground truth to approximating the ground truth using simplicial complexes. Okay? We've also seen that this idea of simplicial maps between simplicial complexes can be used to approximate any continuous function between the geometric realizations, right? So what we saw was that sort of any continuous function from the geometric realization of K to the geometric realization of L is homotopic to some right? In other words, if we start with your complex K, you know, and if you subdivide it enough, right? If you subdivide it a bunch of times, as we explained before, then any G is going to be, you're going to be able to deform it to some, sorry, to the realization of some. Maybe that this is more informative, yeah. To the realization. Yeah, that makes more sense. So again, just to say it out loud, simplicial maps are given at the level of simplicial complexes, right? And the sort of point that defines them is that every time you take a simplex, say x0 through xn or xk, then its image is entirely defined by what happens in the vertices, right? So that was sort of the first idea. And then the second idea was that any continuous function now between the geometric realizations, now these are sort of continuous objects, right? So locally linear objects. So if you give me any function here, then it can be up to deformation approximated by the subdivision of something simplicial that looks like this. And this is what we called the simplicial approximation theorem. Right? So we can now approximate continuous ground truths, and we can approximate simplicial maps, continuous maps via simplicial maps and subdivisions. Okay, great. So now I'm gonna lean on the computational activity we did last time. So allow me to, I'm gonna keep this. We're gonna do a little table over here. So my table is gonna have the sort of shape of the ground truth in one side. I'm also going to have the sort of a data science question on the data. And here we're going to have a computational gadget. And I'm going to try to fill this table for you. Okay, so the first thing that we think of in the shape of X is perhaps its connected components. Right, so these are sort of the pieces in which the data, in which the space splits. Okay. The data science question on X is not connected components, but clusters. Right, so these are, so if we think that the data has been sampled from the ground truth, then we're looking for sort of the distinct pieces of the data. Okay? And what we saw in the computational activity is that the clusters of the data can be approached using the zero eigenvectors of the graph Laplacian. Correct? So what we saw was that, if you had your data, the discrete points, then you can build on them things like Rhibs complexes or nerve complexes. You can do it on the data, or you can use landmarks and then use partitions of unity to sort of extend what you did. And then if you look at the eigenvectors of the graph Laplacian that have eigenvalue 0, then you notice that those sort of distinguish the different the different clusters pretty well. The other idea of shape of the ground truth can be just regions. So, right, so maybe the data doesn't split into clusters, but maybe it has sort of well-defined regions connected via thin bridges. And perhaps the data also reflects this. Right? So here, instead of clusters, maybe we want soft clusters. Right? So we have sort of these two regions over here, and then you want to identify these soft clusters. So regions in the data which may be joined by thin bridges. And what we saw here is that the computational gadget that one can use to encode them is still the eigenvectors of the Laplacian. With small eigenvalues. Right, so hopefully in the last piece of the computational activity, we saw that there was only one eigenvector with 0 eigenvalue for this example, if you did things right. And then the next eigenvector sort of described this region as opposed to that other region. Yep? No, because it would be just one connected component, so it would be constant over that. Yeah? The other shape that we've seen is this idea of one cycles. Right, so maybe when your data looks like this. Correct? And then, if now the data looks like that, then still here, one can use sort of the first few eigenvectors of the Laplacian. We saw that they sort of pretty well describe the circular structure. And then in data science, why would you be interested in things like this? Because if you have a data set that, for example, exhibits periodic structure, like a time series that exhibits periodic structure, then it should be something that goes around a circle. And then being able to parameterize those types of structures is important in some data science tasks. The question now is what happens beyond one cycles? Yeah, go ahead. Yeah, good question. So when we computed the eigenvectors of the Laplacian, we ordered them by the value of the eigenvalue corresponding to it, right? So the first one was 0, that gives you connected components, and then the first few after that, sort of encode circular structure. Right. This is not, yeah, I'm not being very sort of mathematically refined here, but yeah. Okay, now what happens beyond one cycles? And hopefully the number 1 here is suggestive, because I'm using sort of like going around. That's my 1. So how about n cycles or n dimensional holes. Right? So maybe your data doesn't look like a circle. Maybe it looks like a sphere or something that was sampled from a torus. Right? So in that case, if you look at the sphere, then the sphere itself is sort of like a two-dimensional object, and the hole that it has in the middle is sort of a three-dimensional void. Right? So in that sense, this looks different than this picture over here. The gadget that we're going to use to study these types of shape properties is homology. So the graph Laplacian doesn't capture this type of structure anymore. So we need something more refined. And the thing that we're going to use is called homology. And we already started defining some of its underpinnings. Okay? Right. So what is the pipeline for computing the homology of a simplicial complex? So K is the simplicial complex. So what is the first step? Step 1. So the first thing you do is you orient your complex. So we fix an orientation. It's the first thing we do. And let's remember what an orientation is. So this is just a partial order on the vertices such that every simplex is totally ordered. Okay? So pictorially, what does that look like? So say that you have your simplicial complex and it looks like this. Let me put some names to these guys. U0, U1, U2, and U3. Okay? So what is a partial order on the vertices? It's just telling you what vertex is bigger than what other vertex. So for example, you say, let's say that U1 is bigger than U0. So in that sense, the order goes this way. If you say U0 is smaller than U2, then the order goes this way. U1 say that is smaller than U2, or you could say it the other way around. Then the order goes that way. Say that U1 is less than U3, and that U2 is less than U3. So hopefully you can notice that I'm using the actual indices to guide my choice of left or right in the complex. Also notice that since there is no edge between U0 and U3, I don't have to tell you I don't have to tell you what the order is here. However, if I were to do it, I think that's enough. Yeah, there is no edge, so I don't have to tell you how U0 and U3 relate. Okay, so that's step 1. Step 1 is define an orientation, fix an orientation on your complex. Okay. The second step is defining this idea of chains in the complex. So step 2, the idea of n chains. Right, so the n chains, so an n chain is a function is a function phi from the n simplices of k to the integers. So for each n simplex, I'm just going to give you an integer. This is the set of n chains. And there is a, again, just to remind you the notation, there is a very useful way of encoding this set and these functions. And again, let's just remind ourselves what the notations are. Right, so if you let Kn be the collection of simplices in K that have dimension less than or equal to n, then this is called the nth skeleton. Right, so it's got all the zero simplices, all the one simplices, two simplices, all the way up to n. So in particular, Cn of Kz is the collection of functions phi from Kn minus 1 to z. Right, so you take all the functions on the nth skeleton and then forget and not even define what happens in the n minus 1 skeleton. Just the n simplices, that's what's important. The other notational device that we used was that if this guy, right, so you take all the n simplices, sorry, all the simplices of dimension n and lower, remove the simplices of dimension n minus 1 and lower, so this is exactly all the n simplices. So if this guy is equal to sigma 1, sigma 2, all the way up to sigma n, then we write phi equal to phi of sigma 1 plus phi n. Right? In other words, we're writing the sort of expression where here I'm putting the simplices, the n simplices in K, and in front of them I'm putting the integer that you obtain when you evaluate phi at the corresponding sigma. Okay. And again, it's just a notational device. Here I'm not actually adding because these are not numbers. It's just, again, a notational device to indicate that the value of phi in sigma 1 is whatever value I have in front of it. Okay, so why do we need these chains, or why are they useful? I'm going to pick a spot. Let me pick that spot over there. If you see me trying to erase this example, please scream. So we want to keep it for a while. Okay, so so in here we have the zero simplices, right? So K0 is going to be just U0, U1, U2, and U3. U0, U1, U2, and U3. We have the one simplices, sorry, the one skeleton, which is just the one simplices. Let me call these guys perhaps tau 1. And by tau 1, I mean just this edge. Let me call these tau 2. tau 3, tau 4, tau 5, and then the two simplex, I'm going to call it sigma. So tau 0, tau 1, tau 2, tau 3, tau 4, tau 5, and then K2, and then the 0 simplices as well, right? You know what, actually, let me do the following. So instead of writing the entire skeleton, let me just write 1 minus 0 and 2 minus 1. Yeah, there we go. And let me give you an example of what a one chain, or of what one chains look like. In that complex K, right? So a one chain is a function from the one simplices of K into the integers. In other words, you're giving me an integer for each one of these edges, correct? So let's take, for example, so U0, right? So tau 1, tau 4, and tau 2. Right? That's just a chain. What is the meaning? It's saying that tau 1, right, has the value of 1. I guess I didn't write it, but hopefully it is understood. Right? So it is 1 in this guy, 1 in this guy, and 1 in this guy. That's it. Okay? The second chain that I'm going to write is going to be, let's do this guy. Right? Boom. And let's see visually what that is. Right? So tau 4 is this edge, right? It's saying that it appears one time. Then it's saying tau 5, but it's appearing with a minus sign, so I'm flipping the orientation. So now you're going this way, and then you're going that way. And then you have tau 2, but with a minus sign, so you flip the orientation as well. So you get that. Okay? So you're going this way, that way, and then that way. Yep? It is not. It is not. That's a good point. So this is just a chain. And that, yeah, not necessarily, right? So, but that's a good point. Now 2 is actually a chain that is also a cycle. And a cycle. Okay. Yep. Mm-hmm.
Is that a chain because from tau 1 and tau 4 2 is another?
Correct. So that's also a very good point. I'm not using the word path. I'm not using the word path. I'm using the word chain to just say that I have just values on each edge. Whether or not they form a path is another story.
So is the value defined on I1, whatever the first one is there defined value?
Oh, no. I wrote I just to say that this is the first chain I'm going to consider.
Yeah, that's what I'm saying.
So the value on tau 1 is 1. So if you don't see any number, it's because there is a 1 in front of it.
What I'm saying is there, if you did the boundary operator on that, is there any defined value?
We can certainly take the boundary of this guy, and we'll do it in a minute. Yeah. The third cycle I want to write down is going to be tau 1 plus tau 2 minus tau 3. Right? So you have tau 1 plus tau 2 minus tau 3. So not only is it a cycle, not only is it a chain, it is also a cycle, but it also is the boundary of these sigma. Correct? And then the last chain I want to write down is going to be tau 1 plus tau 4 minus tau 5 and then minus tau 3. Okay? So that'll be tau 1 plus tau 4 minus tau 5 and then minus tau 3. So it's both a cycle, so it's a chain and a cycle. And the thing that I want to sort of call your attention to is that somehow the chain I have in number 2, meaning this guy, bounds essentially the same hole as number 4. Right? So I guess the idea here is that these two guys bound the same hole. So what happens when I do, say, tau 1 minus tau 4 minus 2? Let's do that computation. Right? Let's check that though. So tau 1 doesn't appear here, so it'll stay as it is. Tau 4 cancels with tau 4, right? Tau 5 will cancel with tau 5, right? And then tau 3 stays, and tau 2 will appear with a plus sign. Okay? For tau 3, because it's this guy minus this guy. Yeah. Okay? So the thing that I want you to notice is that what I got in here is exactly number 3, which is a boundary. So the intuition is that two cycles that essentially code for the same hole differ by a boundary. Right. So that's the intuition. And then the way to formalize what we just did. So here's a chain and a cycle. A chain and a cycle, both of them code for the same hole, and that is encoded, it seems, in their difference being this boundary. So the third step in this homology trip is to define the boundary operator to formalize what we just did. So step 3, build boundary operators. So the boundary operators are these delta n's that go from n chains to n plus n minus 1 chains, right? Yes. And the way they are defined is as follows. So when you're going to apply the boundary operator to an n chain, right? Say that the n chain is, m1 sigma 1 plus m2 sigma 2 dot 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 mn sigma n. Then the way you define the boundary operator on just on a standard n chain. So this guy here is an n chain. So the first thing we do is we take out the integers, meaning these coefficients, sigma 1 dot 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 m2 and sigma 2 dot 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 mn delta n sigma n. And now I just have to tell you what the boundary operator does to an n simplex. And if you want to evaluate it on a general chain, then you just have to take this linear combination. Okay, so again, I'm going to use this picture. And by the way, all of these material I'm sort of covering today, we've already seen it in one way or the other throughout the course, but I wanted to give you at least a cohesive view of what we've done and where we're going. Okay, so we just have to define now the boundary operator on simplices, and the intuition helps here. So say that you want to define the zero boundary. In other words, you want to compute the boundary of a vertex. Right? So if you look at a vertex, what should be its boundary? It should be 0, right? So vertices don't have boundaries. One boundaries. So say that you have, so now we're going to compute this of, I, j, where ui is less than uj. Right, so the orientation goes like this. Right, so the boundary is comprised of ui and uj, and the way we write it is uj minus ui. So the head minus the tail. And now if you're going to compute the boundary, the two boundary, right, so of a two simplex, so let's say, let me use sigma over here. So u0, u1, and u2. Right, so what is the boundary? Is 0, 1, 1, 2, minus 0, 2. Right? And then one is ready to just define it in general, using just the intuition that one builds from this, and that. Notice that here is where we use the orientations. Okay? We didn't need the orientations to define the chains, but one does need the orientation to define the boundary maps. Right, so the big definition is that if I compute delta n of an n simplex, then the way you do it is by taking the alternating sum minus 1 to the j of the lower faces. So you take u0, un, and you remove the jth component. Another way to write this, that is actually the one we're going to use, is this notation. Right, so this means remove j. And notice that this is exactly what is happening here and what is happening here. Okay? I think I can erase it now. Okay. Yeah, the embargo on this picture is lifted. We can, yeah.
So for here, the U0 to U1 minus U3,
Oh yeah, this is set difference. I'm saying remove this element from this set.
yeah, and the minus one, that total thing on.
It's only on this guy, right? So it's on here, like that,
Oh, okay.
right? Because once you do this, you're gonna obtain an n minus one simplex, right? You're removing one element, you get a n minus one simplex, and what is, yeah, what do the boundaries do? They take an n chain, and then gives you an n minus one chain. And what is an n minus one chain? It's a sum of n minus one simplices with coefficients in front of them.
So this typically applies to only this figure, or it is like.
No, in general, like you have a simplicial complex, an abstract simplicial complex, right? You have it in terms of vertices, edges, and higher dimensional simplices. You can always compute the boundary map of the chains on any abstract simplicial complexes using this formula. The reason why I put the picture there is to sort of explain the intuition of the definitions. Okay? Yep.
Sorry, this UJ.
It means remove uj. Is uj removed, meaning start with u0 through un, and then remove uj from that. Whatever is left, we're going to denote it like this.
So there's no, it's just taking it out.
Exactly. So for example, this guy over here is u0, u1, u2 hat. Yep. Okay, cool. So probably this is where things ended before the computational activity. I want to use these, I want to leverage these definitions a little bit more, okay? So the first thing I'm going to do is I'm going to think about the first boundary operators, so delta 1 and delta 2, okay? So here is the one chains. If I compute boundaries of those, I get 0 chains. And what do I get if I compute the boundary of a 0 chain? 0, right? So you get a 0 here. Because the boundary of every vertex is 0, as we just said. Okay, I want to think about this composition to begin because it's sort of the simplest to understand. Okay? Oh, yeah, this is cool. Yeah. Chains. 1 chains, 0 chains. So I'm going to introduce an idea that is going to help us in a couple of minutes. And it's the idea of an equivalence relation. Okay? And I'm going to use that to understand this picture a little bit better. Okay? How many of you know what an equivalence relation is? An equivalence relation. Some of you, okay? It doesn't hurt to remind us what it is, right? So let's do a parenthesis over here. So given a set, S, a relation, I guess not empty, a relation on S is another set inside of the Cartesian product, right? Which again is not empty. So again, whatever pairs I have in here are just saying that the entries are related. So if R1, R2 is in R, we say that R1 is related to R2, or R1 squiggle R2. Okay, so that's all it is. There are many types of relations, and one that it's useful to have is called an equivalence relation. Okay, so a relation R inside of S cross S is said to be of equivalence if three things happen. If the relation is symmetric, that means that if R1, R2 is in R, then the reverse is also in R. Using this squiggle language, R1 squiggle R2 always implies R2 squiggle R1. Okay. Is reflexive. Meaning that S is always related to S for all S in S. All points are related to themselves. And the third thing we want is transitivity. Meaning that if you have that, R1 is, let me not use R's, let me use S's. So if S1 is related to S2 and S2 is related to S3, then S1 is related to S3. Right, so that's what, so any relation that satisfies those three properties is called of equivalence. Let me give you an example, or let me give you two examples, and we'll see if these are of equivalence. So the first example, I'm going to let my set X be, let's say, the natural numbers, right? So 1, 2, 3, and so on. And the relation is going to be, say that n comma m in n cross n, such that n divides m. Okay. Okay, so if you want to see if a relation is of equivalence, then you just check, right? Is it symmetric, right? Meaning that if n divides m, does it follow that m also divides n? No, because 2 divides 4, but 4 does not divide 2. So this is not of equivalence. Because 2 divides 4, but 4 does not divide 2. Okay? So that's not an equivalence relation. Okay? So what is another relation? So I'm gonna fix a number, let's say Q in N, right? So I'm just a natural number. And I'm gonna let S now be the, yep. Did anyone? Oh, okay. Yeah, someone, I was like, someone freaked out because of Q. Maybe they want N. I don't know. Okay, Z. So let's make S equal to the integers Z, and I'm gonna let the relation be, N comma M in Z are related if and only if Q divides the difference. Okay. Oh, whoa. I guess the sound was an alarm that something was coming. Yep. Oh yeah, you're right. You're right. Thank you very much. Cross Z. There we go. Okay, so this is reflexive, right? Because if Q divides N minus M, that means that one can write N minus M as K times Q. Then in particular, M minus N is minus K times Q, which implies that Q divides M minus N. So reflexive, check. Symmetric. Oh, did I use the wrong name? Yeah, I was wondering if I did it here, but no. Symmetric. Reflexive, yes, because everything divides 0. And transitive also follows. Right, so dividing the difference is an equivalence relation. Okay. So now, what is the point of having these equivalence relations? Is that they allow you to split your set S into sort of pieces, equivalence classes, as people call them. So what do you do? So here's the idea. The idea is, imagine that you have your set S. It looks like we took a huge detour from homology and shape of data, but we'll get back to it. Now imagine that you have your set S, and you have an equivalence relation on it. And let's take a point, a little s in S. Okay? Then what we can do is we can take all the other points in S that are related to this first choice. Okay? So let's put that as a subset. So these are all the guys that are related to the first S I picked. Okay? So we're going to define square S as the collection of all the other S primes in S that are related to the first one I picked. Okay? So this whole thing over here is square S. Okay? Okay, now here is an important fact. Now let's say that I have my S here and I picked, and I formed, its class S squared, and I picked another one, say an element in here. Let's call it S double prime. And now I looked at all the things that are related to it. In other words, this is square S double prime. And let's suppose for a moment that these two sets intersected. So let's say that they have some element in common, namely S prime. Okay? So just to recap, S prime is in here. That means that S is related to S prime. Okay? We're also saying that S prime is also in the class of S double prime. So that means that S double prime is also related to S prime. Okay? But the relation is symmetric, which means I can change the order by saying that S prime is related to S double prime. Okay? And if S is related to S prime, and S prime is and S prime is related to S double prime, then by transitivity, S is related to S double prime. Right, so from here we get S related to S double prime. In other words, S double prime was in here all along. Right? So it means that this guy wasn't just this, in particular, it was all of this. Right? So we can erase that. And it's just the class of S. In other words, by looking at these sets, which again we're calling equivalence classes, what we're doing is we're subdividing my set S into non-overlapping regions. Right? Into non-overlapping regions, because if the region from S, if that overlapped with something from here, then it would immediately just swallow the entire thing. That's what we just saw with S double prime. So we're dividing S into, again, non-overlapping regions. So the remark is that the equivalence classes S split into disjoint subsets. Okay? And notice that in order to show this remark, we used that the relation was of equivalence. We used that I had the symmetric property, and I used that I had the transitive property as well. So if you don't have that, this is not true necessarily. Okay, let's get back to data. Yeah, go ahead. Okay, cool. So there's another equivalence relation that is very useful in graph theory and in data analysis, and it's the following. So suppose that G is a graph with vertices and edges. Okay? Undirected graph. Right, so maybe I have vertices like that and edges like so. And maybe there's another collection of edges over here and vertices. Okay? So I'm gonna define the following equivalence relation. I guess I'm giving away the punchline, but I'm gonna define a relation of the vertices, and I'm gonna show that the relation is of equivalence. The relation is the following. I'm going to say that vertex X is related to vertex Y if there exists a sequence of edges with consecutive endpoints connecting X with Y. correct? So again, the relation is x is related with y if and only if I can find edges with consecutive endpoints connecting x with y. We can define them as paths, indeed. So let's say x is related to y if and only if they are connected via a path. Okay. So in particular, x is connected to itself. That's sort of the vacuous statement. If x is connected to y, if there is a path like this, then y is also connected to x because the graph is not directed. And if x is connected to y and y is connected to z, then by concatenating the paths, we get that x is also connected to z. So that gives you an equivalence relation. Okay? And let's think about what the equivalence classes look like. So they're just the path connected components of the graph, right? Yeah. So we call them, the name we give them is path connected components, right? So this is one equivalence class, and this is going to be another equivalence class. Okay? So the equivalence classes are exactly the same as what people call the path connected components. And as we saw, these can be detected using the zero eigenvectors of the graph Laplacian. Okay. Let me now go back to homology. Okay. Okay, so back to homology. Yeah, go ahead.
When we say, when we're talking about the graph Laplacian, we're
Mm-hmm.
talking about the Rhibs complex
The
dimension and
let's parse that. So the graph Laplacian can be defined for any weighted graph, right? You only need vertices and edges that have weights. What we did for data was to construct the Rhibs complex and then use the underlying graph and then put some weights that made sense. Okay. So the thing that I want to say now is let's now consider the one chains of a complex. So now K is a simplicial complex. Then we have the boundary map to Z0. And then, so this is 1, and this is 0. Okay? So here's the first statement that one can make. So let UI and UJ be zero simplices. Right? So these are vertices in the complex. Okay? Then how do I write this? Then U0, yeah. Then UI and UJ are in the same path connected component of K1 if and only if ui minus uj is equal to delta 1 of tau for some tau. So let's parse this statement. So what I'm saying here is start with a simplicial complex, right? So it's got vertices, edges, triangular faces, and higher dimensional simplices, perhaps. So I can form the one chains, I can form the zero chains, and I can form the boundary maps as we defined them earlier. What I can also do is I can take two vertices inside the zero skeleton. Okay? So I take those two vertices, for example, this is the Rhibs complex or whatever. So I can ask whether or not these two vertices are in the same path connected component of the underlying graph. Okay? So the same question we asked in here. If I only look at the underlying graph of the complex, can I say that they are in the same path connected component or not? And what I'm saying here is that the vertices are in the same path connected component whenever the difference between the zero chain I get by taking their difference is actually a boundary. Okay? That's what I'm saying. If tau is confusing, this is just a chain, a one chain. Okay? Does this make sense?
Yeah, so you're saying like the tau, so for example, with our example,
Mm-hmm.
the tau you're talking about is the four connected like little vertices, and you would take the total border of that, like those concatenate together.
Yep.
To get that.
That would be your.
Probably. So I mean, let's see at least the direction in which I can say that if they are in the same component, then they differ by a boundary. Okay. And that's the last thing we'll do. Okay, so say that U0, the UI and UJ are in the same path component. Right? So what does that mean? It means that there exists a path, U I0, UI1, UI1, UI2, UI n minus 1, maybe not n, let's use k, minus 1, UIK, with UI0 equal to UI and UIK equal to UJ. Right, so this is a collection of edges connecting UI to UJ. Okay? So I'm gonna let tau be the sum. Right, so it's just a chain. So 1, I2, blah, blah, blah. K minus 1, UIK. And let's see what happens when I take the boundary of this guy. Okay? right? So what is the boundary now of this one chain? So we'll just do it, right? So is the boundary is the sum of the boundaries, first of all. So it's delta 1 of ui0, ui1 plus delta 1 of uik minus 1, uik. And then what is this? This is ui1 minus ui0 plus ui2 minus ui1 plus. So this is the first term, this is the second term, and then the last term is uik minus 1. And then by math, this cancels with that. These cancels with the next. And I think these cancels. And the only guys that survive are uik and ui0, which we had said were uj and ui. Correct? So we essentially took, as sort of Joe, right?
Yeah.
As Joe suggested, right? Take a path that connects them, and then just take the sum of the edges as the one chain, and then you'll see that the vertices will cancel out, leaving you only with the endpoints when you compute the boundary. Okay? So all of these to say that if you look at 0 chains and 1 chains, and this boundary operator, this recovers connected components, path-connected components, just like the graph Laplacian did. So in particular, the other ones, the higher ones, hopefully will detect the other holes in the space. Okay? And that's what we'll do on Wednesday. Okay, that's it.